this up a while back, so it may not be accurate on current cars, but the Porsche 918 Spider can go from 0 to 97 kilometers per hour in 2.5 seconds. The reason I did 0 to 97 kilometers per hour is because that is 60 miles per hour, which is typically the time that we report. And but I did kilometers so that we had to look at some different units right here. So they'll do this to us a lot in calculus. They will give us a graph and they will label an axis t and they will label the other axis f of t or something like that. And then they will not put minutes or hours or seconds or whatever else on the graph. But they'll give you a statement that says the graph above gives the speed f of t in kilometers per hour of the car after t seconds. So I give it to you in a sentence. My suggestion would be to label that on the graph. So what goes along the t-axis, or that horizontal axis here? That is seconds, right? So, and then what goes on that vertical axis right there? That is kilometers per hour. Now, there are going to be some major conversion issues right here that we are going to just rely on the internet for, because we're not going to get into something this complicated. But what's the issue with our units that we have here? They're not to the same scale because I've got seconds on the bottom, and I don't have kilometers per second over here. I got kilometers per hour, so those units don't even match. Which means that when we start doing some different things, we're going to get things like kilometers per hour per second, which is not how anybody would ever report this. So we will probably just Google how to convert it. I mean, I know how to convert it. I just don't want to spend that amount of class time on it. So let me change this so it has two next to each other, and let's go over one more. Okay, so for this, 13 says estimate the car speed after 2 seconds. So 2 seconds, that'd be right here. What do you guys think the car's speed is? Okay, what'd you say, Lola? 91. Now, how'd you do that so fast? We didn't make a tangent line or anything. Didn't do any math. Okay, this graph gives us speed, right? So all you've got to do is look over here. Oh, right over here. Oh, we're about at 91, right? Did the graphs that we were looking at yesterday give us speed? They gave us distance, right? So if we wanted speed, we had to find a slope. But this graph gives us speed. So if they ask us for a speed, we just have to look at the numbers. Okay, so knowing that, what about 14? Who can tell me at what time on the interval from 0 to 2.5 is the car traveling at the highest speed? What do you think, Michael?
The car's traveling at the highest speed when t equals 2.5.
Perfect. Because we're not looking for slopes, right? We are just looking for the highest, when this graph is the highest, this gives us speed. So the graph is the highest right here at the end of the graph at 2.5 seconds. So that is the highest. Now, now they're going to ask us about something different. They're going to ask about the car's acceleration. Okay. How many of you have had physics? Some of you took physics online, right? Was it AP or was it like school science math? That's probably the better option, actually, there. Because kids have taken NCVPS AP physics before, and I don't know that they've ever made it on the test. So, but when we're talking about acceleration, that is the rate at which speed is changing. Okay, so acceleration is going to be measured typically in something like feet per second, or miles per hour, or in science context, you're probably going to do do metric systems. So like meters per second is going to be more common. Here we're going to get some weird units. We're just going to Google it to convert it. Here, so we're supposed to estimate the car's acceleration after 2 seconds. Now, if I'm looking for acceleration, I am looking for the rate at which speed is changing. What do I need to do to estimate that? Now I'm looking at slope, right? So what I would do is I would draw myself in a little tangent line here. I would try to come up with something close to some grid lines. A guess. Yeah, this is a true estimate here. Earlier, on 13 we were estimating because it wasn't perfectly on the grid lines, but we're pretty accurate on that. This is going to be a little further off. I'm going to do like right here. We'll go to right here. So this point right here would be, I guess we're going up by 0.2. So that'd be 0.6 and 70. And then this point right here would be, oh gosh, I probably shouldn't have done that. Because that's like 2.2, 2.4, 2 point. Actually, I guess that is about 2.5. And 100. Something close to this. So if we're looking for slope, we're going to do 100 minus 70 over 2.5 minus 0.6. And I forgot to tell you get calculators, so I'll just do it real quick here for you, and because I don't want to drag them out. We don't really need them for the other stuff we're doing. So we got 30 over 1.9. And that is, the top is kilometers per hour, and the bottom is seconds. So we got 30 divided by 1.9. We're going to get 15.789. This is in kilometers per hour per second. Now, technically that is an answer. Those units are horrendous, and you would never like see somebody report that in that way. It is maybe a little bit helpful to think about, though. That means every second that goes by, this car is going about 16 kilometers per hour faster at that point. So if we just go over here, let's just go give it a quick Google. 15.5 or 789 kilometers per hour per second to, let's do meters per second. Oh, I did that wrong. That X. Well, it did anyway. So we got this is going to meters per second, 4.386 meters per second squared. For that. Okay, so the next question says, at what time on the interval does it look like acceleration is the highest? Where do you guys think? What do you think, Avid? Okay, right here, somewhere in this part. So maybe 0.2, let's say, like right here in this first little bit. Right there. So about 0.2 seconds. Okay? If you have ever ridden in a fast car, this should make sense to you. Because if you have ever ridden in a fast car, whenever you take off, it's that initial amount that like throws you back in your seat, right? So if you're in something really fast, it's going to throw you back in your seat. Or if Hunter Hyatt is driving, no matter what car he's driving. Any car he drives is a race car, I think, these days. Some of you may drive the same. Maybe all teenage. It might just be a characteristic of teenage boys. That any car you drive can be a race car if you try hard enough. But that throwing you back in the seat. I remember whenever Miss Ball first got that Model S. It was an S, right? S is that first one y'all had, Braden. She took us to lunch and we pulled out on the bypass. And I've never been in quite such a car. If you have not ridden in an electric car that's really fast, it's like instant speed. It is way different. Like my dad always has, like growing up, my dad and my uncles like always had, Camaros and different things like that. But this is different. It was like really throw you back in your seats. She stopped when she got pretty close to the speed limit. We weren't going 100, but it was really fast. So, like, whenever you're taking off in a fast car, you're going to experience that acceleration more at first, and then you're going a lot faster over here at the end, but you're not experiencing that acceleration quite as quickly, right? You can try this in your own car safely, but if you take off kind of fast, like your car, if you push don't try this in your own car. But if you were to push the gas pedal all the way down to the floor, right, it's going to accelerate more quickly at first, and it's going to have a hard time, right, after that. Like, your 0 to 60 speed is going to be a lot higher than your 60 to 100 speed, which you are not going to try because 100 is too fast, and you shouldn't do it. At point 2, if we drew us a tangent line in here, because our next question says how many g-forces would you have? Okay, so g-forces is 1g, it was on the other slide, but 1g is 9.8 meters per second squared. On Earth. If you were on the moon, it would be different. You have different gravity there. But this is your acceleration due to gravity. So if we did a slope for this line, which let's use 0.2 and 20. And then let's use where we hit a grid line or close to it. Right here is pretty close. Right there, that point is 1.2, 100. So if we're using those two numbers, 0.2, 20, 1.2, 100. And so we got 100 minus 20 over 1.2 minus 0.2. So we will get 80 divided by 1, which will give us 80. But remember, we're in those really weird units. We're in that kilometers per hour per second. And then rather than spending the next 10 minutes explaining how to do that, I am just going to go Google that real quickly so that we can see. Sorry, like that. So you can still see it. Let's do 80 kilometers per hour per second. 22.22 meters per second squared. Go back full screen on this. So if you want to know how many G's, that's your acceleration. You would do 22.22 divided by 9.8, and you're going to get 2.267 G's. And that, unlike you would have on a roller coaster, you might have G's in all different directions. You could have up, down, side to side. In this case, that direction is that what's sitting you back in your seat, which is throwing you back in your seat in that case. And this is pretty high for a car because this is a car that will go very fast quickly. I don't know that any of you have one of these to test it out. The key is probably pretty close, but not quite the same. Okay. All right. So there's another question, but I think we're going to stop on that so that we don't spend too much time on this. Our notes are real short for the end of class today. And we get out here at 11:45, right? It's throwing me off that it's not 11:20, which is the regular schedule. I want to look at the assignment you guys had last night. The numbers that you can kind of rule out. So when you're looking at x equals 0, right here, at that point, the easiest one to rule out is answer choice D. Why could you throw that one out? This slope is negative and D is a positive number. So that definitely has to be the case. Then, like, I have picked one where the tangent line is almost the line itself, which makes it a little hard to draw in. But because, like, right here, I picked a weird point. It's almost like at a point of inflection, which makes it weird. But you'd have something like this. If you think of a graph that's got a slope of -2, that looks like this, down 2 over 1. If you could kind of draw. Is that the same slope? No, that's too steep. Down 1 over 1 would look like this. It's not horrible, but down 1 over 2 would be more like that. I think that one's the closest to what we're actually seeing there for that. A lot of times what you'll see, the other number you see, I should go back and change that, where they'd also have like a 0 slope in there as an option. Like if I had -2, -1/2, 0, and 1/2, might make it a little better question where if you put B, that's probably the next best answer here. Okay. What about 3? What are you guys getting there? 3? 3 feet per second squared. Or those units, you can also do feet per second There. They're the same because if you have feet divided by seconds and you divide that by seconds, right? Feet divided by seconds, you could do this. This is like seconds over 1, right? And then what do we do with fractions? Flip the second and multiply. So feet over seconds times 1 over seconds. And then in the top, 1 times feet is just feet. And seconds times seconds is seconds squared for that. Which is I don't know how much you guys had Mr. Blevins for chemistry. I don't know how much he did like math with units like that, but units can work just, I don't know what went on up there. But if you haven't seen this is especially anybody interested in engineering school. I know my husband always says this is one of the things that was like most useful to him in engineering school, was that like the units can almost like solve the problem for you because they work like a variable. So feet per second squared and feet divided by seconds are the same thing there. Okay, and all we're doing on that one is just, since you want 9, you're taking 8, 35, and 10, 41, and finding the slope. You want to pick those places closest to it. All right, and then let's see what we got over here for 4. 4 was not a multiple choice question, so if you got A, B, or C, you're wrong. So if you circled 1, you're not correct. But for A, these are exact answer problems. The reason that you're going to get an exact answer for these are because you got straight lines, right? This is really like a pre-calculus problem. We don't have curves. So for A, you should get 10/3 or 3.3 repeating. You're just finding the slope of this line segment. What do you get for B? 0. That's one you can look at and see. If you got a horizontal line, what's the slope of a horizontal line? 0. You don't actually have to calculate it. And then this last one, you should get 15 for that. Okay? Questions? All right, and like what you're doing there is you're just doing, you know, like here, you're doing slope. This is the point 820, and this is the point 1050. So you're just doing 50 minus 20 over 10 minus 8 to get that. So 30 over 2 is 15. We're just doing that slope. Okay, this one's really mostly just a sort of a, you can kind of think about what the graph would look like for this. They're saying which of the following times is the speed of the function of the pumpkin most likely the greatest? Here's a question that we haven't talked about yet. What's the difference between speed and velocity, my physics people? Or anybody, but
Velocity has direction, it's just a vector, speed is just scalar, it doesn't have direction.
very good. No direction on speed. So velocity can be positive or negative. You have velocity going, like if you're going up, you have positive velocity. If you're going down, you have negative velocity. But speed does not have a direction. That is why we call what's in your car a speedometer, right? It's telling you how fast you're going. It does not tell you anything about the direction that you're going, right? In this case, what did you guys get for this? A, and it is going to be that like initial launch. That's when you're the steepest section, right, of this graph, and that should make sense. Now, if we kept on going with this graph, it should actually probably be mirrored on the other side. Like here, this is really only showing us going up, but eventually it's going to come back down and it's going to hit, gravity is going to have it hitting pretty much the same speed on the way back down there. So it's going to be parabolic. Possibly faster depending on what height that, well, it's going to be the same because it was launched from 0 feet, but it was launched from a higher point. It could possibly go faster. All right, and 6 is probably the hardest one. What do you guys think about 6? B or D? Which one is B? Okay, what do you think? D? Okay, D. All right. Let's draw us a graph for this because I think it's confusing, but they love to do this stuff and they love to use like this theoretical stuff, which I think is really difficult sometimes, but graphs can help. The position of a particle on the x-axis is given by x of t, where x of t is measured in meters and t is in seconds. So we got t, we got x of t. This is meters, this is seconds, right? And we're going from 0 to 20. If y equals x of t is a linear function, which of the following would most likely give the best estimate of the speed? There is a condition where both B and D can be correct, okay? Because this is, we're saying the x of t is linear, right? Straight, or it has to be not, I guess it could be a horizontal line, but I'm thinking more slanted line here. And when I'm thinking slanted line, like the most common thought would be to have a slanted line that looks like this, right? B and D would both be correct in this case. Because if I pick, like if 5 is right here, and so if 5 is here, then over here on the y-axis, we would call that, because this is x of t, we'd call that x of 5, since we don't really like know a number, right? So like the coordinates of this point are 5, x of 5. like that. So what are the coordinates of this point right here? 0, 0 on what I've drawn. So if I do slope formula, because slope is going to give me the speed, that's going to be meters per second, right? I would do x of 5 minus 0 over 5 minus 0, and that would give me x of 5 over 5, right? Which would be answer choice B. But would it also be answer choice D? It's also the slope of the line at that point, right? Now, that's for this specific line, which is what my mind goes to most often, because I almost paused there for a second because I haven't seen this since last year and thought, do I have 2 correct answers? But I do not, because did they tell us that the line goes through 0, 0? They did not. It could be that the line looks like this, right? So if the line looks like that, then right here's the point we're looking at. But is 0, 0 and the slope, is that going to give us what we're looking for? That's not going to be how fast this is changing, right? So you would just use D, the slope of the line at that point. Also, there is no correct answer for this question. Why is there no correct answer for this question? I put y of t on that last part, and that really should be an x of t right there, because that's what I'm using the whole time, and y would be a different function, which we have not talked about. So change that to an x. It should have been. That's just typo there. Let me close that out and go change that. Okay, questions? This is just sort of like an introduction to get us thinking about things. If you're still like a little bit iffy on this, it doesn't make perfect sense, that's okay, because this is really just to kind of get us thinking about some of the topics that we're gonna consider in this class. It is not to be an expert on it yet, because what we're gonna do is probably spend the next like 3 units learning how to find the exact correct answers to those types of questions. So if you feel a little shaky on it, don't worry, it'll be fine. Let me go fix that so that it won't be wrong next year. So we are going to take a few little notes. I'll pass those out. Let's make that an X and save it. And I almost didn't do these this time because I think you might already know most of it. But it's okay, it won't take us long to run through. Because since we have started doing AP Pre-Cal, we actually do some limit notation. So you have seen the limit notation before. That first unit that I gave to you is like an intro. That's just like a little intro section to get us thinking about some things. Unit 1 of AP Calculus is limits. You have seen limit notation a little bit, but we have not looked at it in super great detail. So we are going to just talk about just notation today. We're not really going to do any limits really today, just to make sure we understand how to like write it and say it and what it's asking us for. Then in the next sections, we will be looking at actual like finding limits, different ways. So I am going to kind of explain a little bit what a limit is, given this definition here, which is actually technically the informal definition of a limit, which is scary because that means there's a worse version of this. That means there's a more detailed, more precise mathematical definition. The first year I ever taught calculus, I tried to teach it. It's like an epsilon delta thing. I can't remember it honestly, but it was in the textbook, so I tried to teach it, and then I realized I definitely don't have to teach that like formal definition here. So this is the informal definition, which is going to be plenty good enough for us to understand the things that we need to understand. It says, given a function f, the limit of f of x as x approaches c is a real number, capital R, if f of x can be made arbitrarily close to R by taking x sufficiently close to c, but not equal to c. If the limit exists and is a real number, then the common notation is limit as x approaches c of f of x equals R. Okay, sounds just like gibberish, really, whenever you read through it. But what I want us to do is draw a graph for it to help us see kind of what it's talking about here. So I'm going to do first quadrant graph because the first quadrant is the easiest place for us to graph. And we're talking about f and f, or we're talking about x and f of x. So I'm going to label this axis right here as x, and I'm going to call this one right here f of x. And it tells us we have a function called f of x. And it really does not matter all that much what type of function I draw here. I could make a sine curve, I could make a parabola, I could make whatever. I'm just going to go with, you know, some sort of squiggle of sorts, and I'm going to call it the function f of x. Okay, and so it tells us that we've got a function f, and we've labeled our axes. It says the limit of f of x as x approaches c. So that means there is some number on the x-axis called c, right? C is just a variable. So I'm gonna put me a c right here. All right, and then it starts talking about this number, capital R. So what's happening here, like right here at this point where my x value is c, then that means c is the x coordinate of that point, right? We're saying here that capital R is the y value of that point. So we could let me use a different color. We could call this over here R, right? That's this is the point C, capital R. Now, for a limit to exist, you actually can have a closed circle or an open circle right there. It doesn't have to be a closed circle. It could be like a hole in the graph at that point. And we'll talk about that more when we talk about actual limits. But what it's saying is that as x approaches c, f of x can be made arbitrarily close to R by taking x sufficiently close to c. What it's saying, as my x coordinate gets closer and closer and closer to c. So like if you think of this point right here, you're getting closer and closer and closer to your x value becoming c. Your y value is going to get closer and closer and closer to R, right? You could have a hole right there. It's still getting close to that point, right? This is like whenever your parents tell you not to touch your sibling again, ever, or you are going to have some ridiculous consequence, and you do this. You get as close to them as you possibly can. Anybody ever been around small children or been the small children yourself where you're told not to touch something and you just get as close as you possibly can, but you don't touch it? That's kind of what it's saying right here. You're approaching, your limit is approaching that item you're not supposed to touch or that person you're not supposed to touch. But you may or may not actually get there. In the case of your sibling, chances are you for sure are going to actually touch them again. And everybody's going to lose their minds, or at least at my house. That's how it seems to work. So, this is what we call like the informal definition here. And so what it's telling us here, like we're going to be using this notation. Right here tells us what the X is doing. X is approaching C. The R right here, you might want to make a note of this. This is the Y value that you're approaching. So the Y value at that point. And when we do some more of these with graphs and stuff tomorrow, we'll talk about that more in depth. I don't expect you to like understand that completely here today. So, our first several examples, I want you to take this, we're going to take this limit notation and we're going to write it down in words. Raleigh, you with us? Raleigh. Oh, he's alive. Okay, good. All right. We got limit as x approaches 5 of x squared plus 7. So whenever you read this, you got a couple options on how you can read that. I usually do this. I say the limit as x approaches 5 of x squared plus 7. However, these two phrases, as x approaches 5 and of x squared plus 7, are kind of interchangeable as far as the order that you say them. Because I'm only going to write this down one time because it's silly to do this over and over again. It takes too long. But you could also say the limit of x squared plus 7 as x approaches 5. There. So this, you should be fairly familiar with this because we use limit notation to talk about like asymptotes in pre-cal. So it shouldn't be totally foreign. There are just a couple things I want to remind us of. So what does it mean if we look at example 2? If I've got this negative behind the A, what is it? Coming from the left. So like this one would be the limit as x approaches A, I'm going to shortcut that a little bit, from the left of g of x. Right? And so that little bitty negative right there is where we get that we're only coming from the left side for that. So we just need to remember that if we see positives or negatives behind the number that we're talking about, that tells us left or right. What about the first one? Which direction was it from? It didn't have a positive or negative. So that means both. You have to have both sides going to the same spot. So if it looks like example 1 where you just have a 5, there's no positives or negatives behind, that's both sides. This one would only be left. Let's just, for this one, what do you see that looks different on this one? We got this little positive right here. That tells us from the right. So this one would be the limit as x approaches 1 from the right of 3x plus 2 over x minus 1. And again, it is because That little positive right there tells us we're only looking at the right side. Okay. And I don't even know if we need to write this one down. What's the only difference on this one? There's no number, right? We're just approaching infinity. That just means way out at the end of the graph, right? There. We could also approach negative infinity, which means way over at the left side of the graph. That one actually might be the one you're most familiar with because that's the one we use the most often in pre-cal, right? Because we were talking about like end behavior a lot of times with that. So this is limit as x approaches infinity of natural log of x plus 2. We'll move on quickly. Let's write limit notations for word expressions, okay? Most of these are fairly simple given the function f, where f of x equals square root of 3 minus, or square root of x minus 3. Find the limit of f of x as x approaches 3 from the right. Okay, so we will always make sure we got a limit. What does x approach? 3. Do I need a positive or negative behind it? Positive. And then always make sure you're doing the limit of something. I would just do f of x. I think if they use function notation, it makes it the easiest to name that way. But it is an option to do it this way as well. Limit as x approaches 3 from the right of square root of x minus 3. Don't do x equals square root of x minus 3. Like you don't want both of those things there. Okay. 6, find the limit of the function f of x equals e to the 2x plus 3 as x approaches 9 from the left. So anytime we're doing a limit, we start off with the limit. You're looking for what x is approaching. X is approaching 9. Do I need anything behind that? Negative right here. And then you got options. You can do, I would just do f of x, or it would be also acceptable to do x approaches 9 from the left of e to the 2x plus 3 if you'd rather. Okay, easy enough. Makes sense. Let's move on to the next one. I hope you don't run into this, but it could happen where they've used that definition. For a function f of x equals x plus 1 over x minus 3, f of x can be made arbitrarily close to 3 by taking x sufficiently close to 5, but not equal to 5. Okay, so I know it's a limit just because we're getting like arbitrarily close. Think of you're getting closer and closer and closer to something, which is what you're doing when you're doing a limit. All right. So I know I'm doing a limit, and I know underneath my limit has to be x approaches something. That's always the case. What is x approaching here? It's not 3. It's 5. X is sufficiently close to 3. So you're looking for that piece right there that says what x is doing. So x is approaching 5. But the 3, this is different than we had on the others. There's a 3 there. Okay. Your function is f of x, right? So I could just put an f of x right here. In this case, 3 is the answer. 3 is the y value, right? So you would put equals 3. The first two that I gave you didn't have answers. They weren't telling you what the limit was. They were just giving you like limit expression there. But this one should look like this. And you could also do it with x plus 1 over x minus 3 instead of f of x if you'd rather. If you find that what x approaches first, that'll make it easier to, the other number is probably what it's equal to, if you get that there. As x approaches infinity, the value of the function f of x equals 5 over x approaches 0. This is not explicitly say it's even a limit, but that as x approaches infinity, you can only do limits for x approaches infinity. Because can you ever actually get to infinity? You can't plug infinity in, right? It's not a real number. It's more of an idea than it is a number. So I know it's going to be a limit, so I have a limit. X approaches infinity. I'm still just going to call it f of x. And in this case, it tells us that that approaches 0. So that's your answer. That's a equals 0. This one also has an answer there. If you have an extra leftover number you haven't used, it's probably the answer there. And then our last one, as t is made sufficiently close to 6 from the right, the value of a function g can be made arbitrarily close to 2. Now, this one doesn't use x's. What letter are they using instead of an x? T. So we're going to do not the limit as x approaches in this case, but t approaches. What is t approaching? 6. Okay. What's the name of the function? G. And I'm going to call it g of t because clearly t is what we're plugging in since t is the variable that is approaching, right? Even though they only called it here g. That's something that, like, I don't know how much we did in pre-cal, but sometimes I'm more likely in pre-cal to call it like f of x, but you can also just refer to the formula as f. You don't have to say f of x. So, but when you do it here, you want the of t part. And what's the answer to that? That equals 2. Oh, you are exactly right, because what part was I skipping? From the right, which means we need a positive behind the 6. Good catch. I feel like I'm ChatGPT. Anybody catch ChatGPT being wrong? If you tell it, it'll be like, oh yeah, actually I was wrong. It knows it's wrong, but it still tells you the wrong thing in the beginning. All right, questions here? All right, we're not going to do an assignment with that because I feel like it's pretty basic. But you are